Hi, we are from Group 1. Today, we will be giving a presentation on our lab enhancements and project. My name is Shalin Ravi Mahindra, and for the lab enhancements, I have chosen to do Lab 4, which is on K-means clustering. For this lab enhancement, I've used the same dataset as the one used in the original lab, which is small_customers.csv. This lab focuses on K-means clustering, an unsupervised machine learning technique that groups similar data points together to reveal hidden patterns. K-means partitions data into K clusters where each belongs to the cluster with the nearest mean, minimizing variance by repeatedly adjusting centroids. The lab's mathematical foundation includes Euclidean distance, used by K-means to measure similarity between points, with the goal of minimizing inertia. To start this lab, I begin by importing the necessary libraries that will be needed throughout the lab. I mount the Google Drive to access files during the lab and set the working directory to the folder containing the relevant files. Then, I load the dataset to start analyzing and applying clustering algorithms. The next part of the lab is data exploration. I included this part in the lab to get to know the data before working with it. After loading the dataset, I display the first few rows to understand its structure and features, including customer ID, gender, age, annual income, and spending score. Next, I generate a statistical summary of the numerical features to get key statistics like mean, standard deviation, min, max, and quartiles. I then check for missing values to ensure data quality and find that there are no missing values in any of the features. The same goes for duplicates. I also create histograms for age, annual income, and spending score to understand their distributions. The age distribution shows a diverse customer base which peaks in the 20s to 30s and 40s to 50s. The annual income is skewed, peaking in the $60,000 to $80,000 range, while the spending score displays a wide range of habits. Then, I use box plots to identify outliers in the numerical features. While age and spending score show minimal outliers, the annual income box plot reveals a potential outlier with a significantly higher income. Next, I analyze the relationships between the numerical features using a correlation matrix heat map. The results show a weak negative correlation between age and spending score, with no significant correlations between annual income and spending score, or age and income. After that, I analyze the gender distribution using a counter plot, which reveals a higher number of female customers compared to the male customers. Next, I carry out data preprocessing to prepare customer data for K-means clustering by selecting numerical features and standardizing them. This prevents larger scale features from dominating the results. I use the elbow method and silhouette score to find the optimal number of clusters. Based on the elbow method graph here, the optimal number of clusters is 2. On the other hand, based on the silhouette score graph here, the optimal number of clusters is 6. For evaluating K-means performance here, I focus on evaluating the quality of clustering done by K-means. I assess it using inertia and silhouette score, then visualize the clusters. Finally, I compare K-means clustering with other algorithms like hierarchical clustering and dbScan. In this section, I address common challenges in K-means clustering and their solutions. For handling different data types, one-hot or label encoding can be used for categorical data, while K-modes or K-prototypes are better suited for mixed data. To deal with outliers, methods like the Z-score, K-medoids, or removing extreme data points can be applied. For large datasets, mini-batch K-means offers a faster, more scalable solution. Lastly, to mitigate K-means sensitivity to initialization, K-means plus is a better technique for selecting centroids. In this section, I'll focus on fine-tuning K-means for better performance. This includes adjusting the number of clusters using inertia and silhouette score to find the optimal value, using K-means for improved initialization, applying mini-batch K-means for larger datasets, and assessing performance with inertia and silhouette score to refine the clustering. Based on this lab, I can conclude that K-means has benefits of efficiency, simplicity, and flexibility. On the other hand, its drawbacks are sensitivity to outliers, dependence on initialization, and limitations with cluster shapes. That is all for my lab enhancements of K-means.
Hello, sir. My name is Darwinsha Kumar, and I'm from group number 1. I'll be presenting on the enhancements done for lab number 5, which is Principal Component Analysis, in short, PCA. So the main reason I chose this lab is because I wanted to refine theoretical explanations in order to ease future students, as well as enhance the data visualization by incorporating advanced comparisons to provide a more deeper understanding of what PCA is and how is it applied in machine learning applications. So PCA is a fundamental dimensionality reduction technique that helps in simplifying complex data sets while preserving the most critical information. This is particularly useful in machine learning applications. So this revised lab includes a structured breakdown of PCA, whereby it explains how PCA projects high dimensional data into lower dimensions while maintaining variance. So this plot shows that explain variance by principal components, and then the role of principal components and their orthogonality in capturing unique variance, as well as the importance of standardizing data before applying PCA to ensure meaningful results. So one of the key enhancements is the addition of explained ratio plot. So in order to understand how much variance each principal component captures, we determine the optimal number of components needed for an effective reduction to minimize unnecessary loss of information while providing computational efficiency. To provide a more intuitive understanding of high-dimensional data structures, a 3D plot has been included, whereby we can observe the original distribution of data before transformation, visualizing analyzed class separability in raw feature space, as well as compare before and after transformation more effectively. So this is the before and this is the 2D version of after. So next we have PCA on image compression. So why this is done, this is a new section demonstrating how PCA can be applied in image compression. So this is done to reduce the number of color channels in an image while retaining its key features. As you can see, the original image is more vibrant, but the compressed image is a bit washed out. This reduced the color channels, but it did not change what the original image means. And then next up, we added comparison using TSNE and UMAP. So what are those? So PCA is a linear method that maximizes variance, making it efficient for structured dataset, whereby TSNE is a non-linear technique focuses on preserving local relationships in data, whereby UMAP, on the other hand, is a fast, effective alternative to TSNE that maintains both local and global structure. This lab provides a more visual comparison for breast cancer dataset, helping users with the best technique for their specific needs. So right here, I've explained the advantages and disadvantages of PCA. So PCA reduces dimensionality, leading to a faster computation, and it also removes any noise and ensures orthogonality between components, minimizing multicollinearity. And the disadvantages are it is a linear method, ineffective, and non-linear data structure for non-linear data structures. That's why we had a new way, which is TSNE and UMAP. So when do we use PCA? New students may ask. So it is used when reducing dimensionality to avoid overfitting to visualize high dimensional data. And it's also a pre-processing step to speed up ML algorithms. And finally, when features are highly correlated and to capture the most important variants. That's all from me.
Hi, my name is Noelia Shuaida binti Sharudin, and I will be presenting about lab enhancement for Lab 7, which is linear regression. The first enhancement I made are polynomial regression, ridge, lasso, and residual analysis. To begin, I create a synthetic dataset. This helps simulate real-world scenarios where we want to model a relationship between input and output variables. I generate 100 random values between 0 and 10 for the input variable x. The target variable is y, follows a quadratic equation. Next, I split the dataset into training and testing sets. 80% of data is used for training, 20 is kept for testing. Since regression model can be sensitive to different scales, I applied feature scaling using standard scalar from skitlearn. This process normalized the data so that it has a mean of 0 and a standard deviation of 1. It improved model performance, especially when using rich and lasso regression. Now that I have scaled the features, I need to apply a polynomial transformation. Since the dataset follow a quadratic relationship, I transform the features to a higher degree polynomial, which is degree 2, to better capture the underlying pattern. The transformed dataset now include the original feature, x, the squared feature, and a constant term. Next, I calculate the variance inflation factor. VIF measure how much a feature is correlated with other feature. The intercept has a moderate VIF. X1 and X2 have a high variance inflation factor values, indicating strong correlation. After transforming the data, I trained a polynomial regression model. Now, I use the train model to make a prediction on the test data and evaluate its performance. Mean residual show the average error in predictions, and residual standard deviation measure the spread of errors. Mean residual is around 1.9065, which is close to 0, meaning our model doesn't have a large bias. The residual standard deviation suggests some variability in the prediction, but the model captured the quadratic trend well. Once the polynomial regression model is trained, we evaluate its performance using error matrix, which is mean square error, root mean square error, and R-square score. The MSE is 63.5841 and RMSE is 7.974240, meaning the model has an average error of about 7.97 units. The R-square score is 0.9933. Now I introduce rich regression, a regularized version of linear regression that prevent overfitting by adding a penalty term. Rich regression used to reduce overfitting by penalizing large coefficients. So the best alpha is 1. The R-square score for rich regression is 0.9426, slightly lower than polynomial regression, but with reduced overfitting. Now we move to lasso regression, another regularized regression technique similar to rich but with L1 regularization. The best alpha value is 1. The R-score is 0.9426, which is the same as rich regression in this case. And then we visualize the distribution of residual for polynomial regression to check the model's performance and assumption. From the histogram, we can get the residuals are spread around across both positive and negative value, which is expected. And the KDE curve help visualize the distribution shape. Next is residuals versus predicted scatter plot. This step visualize the relationship between residuals and predicted values to assess the goodness of fit for the polynomial regression model. The residuals seem to be spread across different predictive value, which is a good sign. The second enhancement is enhanced residual plot with annotation. This visualization improves the residual plot by adding color mapping and identifying extreme outliers. Color-coded residual means darker red is a higher residual, blue indicate lower residual. Residual should be randomly scattered around 0 for a good model. And the third enhancement is improving residual analysis using Shapiro work and Birch-Pagan test. This could perform statistical tests on the residual of a polynomial regression model to check normality and non-constant variance. Shapiro will test check if residual are normally distributed. If P less than 0.05, then reject HO, means residual are not normally distributed. If P greater than 0.05, it means fail to reject. And since P 0.0617 greater than 0.05, we do not reject HO. After that, Bridge-Pagan test check for non-constant variance. Since P is 0.3277 and greater than 0.05, we do not reject HO, meaning residual appear to have a constant variance. The advantages of linear regression is simple to implement and interpret. Overfitting can be controlled using dimensionality reduction and regularization. The disadvantages is sensitive to outliers and assume a linear relationship and does not fully capture complex variable relationship. I think that's all for me.
Hi sir, my name is Nofar Nabila and today I will be presenting my enhancements to the logistic regression lab, which focuses on applying logistic regression to a real-world datasets and comparing it with other classification models. The objectives of this lab enhancement include applying logistic regression to a real-world dataset and evaluating its performance, using data preprocessing techniques such as feature encoding and missing values, visualizing key insights using correlation heat maps, survival distributions, and ROC curves, comparing logistic regression with alternative models like decision tree and SVM, and analyzing the strengths and limitations of different classification approaches. Logistic regression is a supervised learning algorithm primarily used for binary classification problems. Unlike linear regression, which predicts continuous values, logistic regression outputs a probability value between 0 and 1 using the sigmoid function. The sigmoid function helps in making predictions by transforming input values into probabilities. Logistic regression is widely used because it is simple and interpretable for binary classification problems, computationally efficient compared to more complex models, outputs probabilities which are useful for decision making. However, it has some drawbacks, such as not handling nonlinear separable data well, assuming independent features, which may not always be the case, and being sensitive to outliers. For these lab enhancements, I applied logistic regression to the Titanic dataset. The dataset contains details about passengers, including features such as age, gender, fare, and class to predict whether passengers survived. Before applying logistic regression, I need to prepare the data by handling missing values by filling in missing ages with the median, dropping less useful columns such as cabin, name, and ticket, encoding categorical variables like sex and embarked using label encoding, and standardizing numerical features such as age and fare to improve model. To better understand the dataset, I use various visualizations, including survival count plot, which is a bar chart displaying the number of passengers who survived versus those who did not, helping to understand the overall survival distribution. Survival rates by gender, which is a bar plot showing that the females had a significantly higher survival rate than the males. Survival rates by passenger class, which is a visualization indicating that first class passengers had a higher survival rate compared to second and third class passengers. And also correlation heat map, which is a heat map displaying the relationships between features, highlighting which variables are most strongly correlated with survival. To assess logistic regression, I compare it against decision tree and SVM models. The models were trained and evaluated using accuracy, classification reports, and confusion matrices. As a result, it shows that logistic regression accuracy is 80.3%. Decision tree has an accuracy of 73.0%, and SVM has an accuracy of 61.2%. This shows that logistic regression performed the best overall balancing accuracy and interpretability. To further evaluate the models, I use confusion matrix, which is a heat map representation of true positives, true negatives, false positives, and false negatives, showing how well the model distinguishes between the classes. And also, I evaluate the models using ROC curve, which is a plot illustrating the trade-off between sensitivity and specificity, where a higher area under the curve AUC indicates better model performance. I also examined feature importance in both decision tree and logistic regression model. The analysis showed that the different models prioritize different features, providing insights into the decision-making processes. This is a feature importance plot, which is a bar chart comparing the most influential features for decision tree and logistic regression, showing which factors contribute most to survival prediction. I also visualized decision boundaries of logistic regression, decision tree, and SVM to understand how each model classifies data. As you can see here, logistic regression displays a smooth linear boundary. Decision tree produces more complex step-like decision regions, and SVM creates a margin-based separation, often performing well in cases with complex decision boundaries. These visualizations help in understanding how each model separates data and makes classification decisions. To summarize, my lab enhancements included applying logistic regression to the Titanic dataset, enhancing data preprocessing techniques, adding visualizations to clarify concepts, comparing logistic regression with decision tree and SVM, evaluating model performance using coefficient matrices and ROC curves, discussing the strengths and weaknesses of different classification models. As a conclusion, logistic regression is a powerful yet simple model for binary classification. Through my enhancements, I demonstrated its effectiveness in real-world applications while also exploring alternative models for comparison. These insights help in making better classification decisions based on different datasets and use cases. Thank you.
Next, for our project, I've completed the data exploration, feature engineering, and data visualization part. To start this project, I begin by importing the necessary libraries that will be needed throughout the project. I mount Google Drive to access files during the project and set the working directory to the folder containing the relevant files. Then, I load the dataset to start analyzing and applying the necessary algorithms. Next part of the project is data exploration. I included this part in the project to get to know the data before working with it. After loading the dataset, I check the dimensionality of the dataset, which shows the number of rows and columns. Then, I display the first few rows to understand its structure and features, including station, name, latitude, and longitude. Then I check for missing values and duplicates to ensure data quality, finding no duplicates but some missing values. To handle this, I remove any rows with missing values. I recheck for missing values and duplicates, and the updated data shows none. I also recheck the dimensionality and find it decreased after cleaning. I then generate a summary of the dataset structure, including column names, data types, and non-null counts. Next, I generate a descriptive statistics for the numeric columns, including mean, standard deviation, min, and max values. I check the number of unique weather stations and station names, display the first 20 station names, verify the date range, and identify stations with multiple IDs by counting unique station values for each name. I then generate box plots to visualize the distribution of weather data across different stations. It creates 4 separate box plots. One for precipitation, one for average temperature, one for max temperature, and another for minimum temperature. After that, for feature engineering, I convert the date column to date-time format, extract the year from the date column, and then group the data by year. It calculates the mean of average temperature, the maximum temperature, the minimum temperature, and the total precipitation for each year. The resulting yearly data frame shows the aggregated data. For data visualization, I plot the yearly temperature trends for average temperature, maximum temperature, and minimum temperature from 1981 to 2021 using the yearly data frame with different colors for each temperature type. Next, I create a line plot to visualize yearly precipitation trends from 1981 to 2021 with the x-axis for the year and the y-axis for the total precipitation in millimeters. Then I create a box plot to detect potential outliers in temperature data over the years, showing the distribution with the IQR and whiskers, where points outside the whiskers indicate outliers. I also created a box plot to detect potential outliers in total yearly precipitation, visualizing the distribution with IQR and whiskers, where points outside the whiskers indicate outliers. I then created a line plot to visualize the trends of average temperature and total precipitation over time, with temperature in blue and precipitation in purple, showing the values across the years. After that, I generated a heat map to visualize the correlations between different variables in the dataset. It reveals a strong positive correlation between temperature variables and a moderate negative correlation between elevation and temperature. Correlations between precipitation and other variables are weak. Next, I create side-by-side plot showing the distribution of average temperature with a red histogram on the left and total precipitation with a blue histogram on the right. Then I create a scatter plot to visualize the relationship between elevation and average temperature, with elevation on the x-axis and temperature on the y-axis.
Next, I will be presenting my analysis of climate data using principal component analysis, which is PCA, and k-mean clustering. This project focused on reducing the dimensionality of climate data while identifying meaningful patterns and clusters. Principal component analysis, or PCA, is a statistical technique used to reduce the number of features in a dataset while preserving as much information as possible. This is especially useful for high-dimensional data, making visualization and analysis easier. Before applying PCA, we need to standardize the data to ensure that all features contribute equally. Here, I selected 4 climate features, which is average temperature, maximum temperature, minimum temperature, and precipitation. Next, I apply PCA and reduce the dataset to 2 principal components for visualization. The scatter plot shows how data points are distributed based on the first 2 principal components. The color gradient represents different years, highlighting how climate data evolve over time. The variance explained by PC1 and PC2 is printed below. This tells us how much information is retained. Together, these 2 components explain around 72.7% of data variance. To understand the contribution of each climate feature, I examine the PCA loadings. From the loadings, we see that maximum temperature contributes the most to PC1, while average temperature has the highest impact on PC2. After dimensionality reduction, I applied k-means clustering to group the years based on climate trends. The plot interpretation is each color represents a different cluster, and the years with similar climate patterns are grouped together. I think that's all for PCA. Thank you.
Now that we have explored and processed our data, let's move on to the core of our project, which is developing machine learning models to predict climate risk in Malaysia. Our goal is to accurately predict 2 key climate variables, average temperature, TABG, and precipitation, PRCP. By doing so, we can provide actionable insights for disaster management, agriculture, and also public safety. We evaluated multiple models to determine the most effective approach. These models include linear regression to assume a linear relationship between features and target variables, random forest, and ensemble method that improves accuracy by reducing variance, decision tree, which is a simple but effective model for structured data, SVR to capture complex relationship using kernel functions, and XGBoost regressor, which is a powerful gradient boosting method that optimizes prediction sequentially. To train our models, we selected key climate-related features, which is elevation, higher altitudes impact temperature and precipitation, max and mean temperature, which is influential in predicting TABG, and PRCP, used for both precipitation and temperature predictions. To begin, we ensure that the datasets includes that required feature, elevation. This is done by merging it back into our dataset from a separate data frame that contains unique elevation values for each year. After merging, we verify the elevation is present by printing the column names. Next, we import essential libraries for machine learning, including scikit-learn for model training and evaluation, NumPy for numerical computation, XGBoost for boosting algorithms, and ptTable for displaying results. Feature selections play a crucial role in model performance. Here, we define the independent variable features and dependent variable targets for predicting average temperature TAVG and precipitation PRCP. Missing values are removed before splitting the data into training and test sets. To train our models effectively, we split the data sets into 80% training set and 20% test set. This ensures that the model learns from a portion of the data while being tested on unseen data. We chose 5 different regression models for comparison: linear regression, random forest, decision tree, support vector regressor SVR, and XGBoost regressor. Each model is initialized with specific parameters for optimal performance. To evaluate the models, we define a function that trains each model on the training set, makes prediction on the test set, and calculates 3 key metrics, which are mean absolute error, MAE, root mean squared error, RMSE, and R-squared score. These metrics help in assessing model accuracy. Now, we apply the evaluation function to both target variables, which are average temperature and precipitation. This generates a comparison table of models based on their performance. Here are the results for predicting average temperature. The models are compared based on their MAE, RMSE, and R2 scores. Lower MAE and RMSE indicate better performance, while higher R-squared suggests a stronger fit. To conclude, our machine learning models effectively predict temperature and precipitation, enabling better climate risk management in Malaysia. The decision tree and XGBoost models perform exceptionally well in predicting temperature, achieving near perfect accuracy. This part demonstrates how data preparation, feature selection, and model training and evaluation come together in developing an effective machine learning model. Thank you.
Thank you. My name is Darwin, and I'll be explaining regarding model evaluation, justification, and recommendations we have from our project that we have done. So in order to compare the models and which evaluation metrics works the best, I have plotted 2 bar charts. One is for temperature and one of it is for precipitation. As we can see, these models are evaluated with MAE, RMSE, as well as R2 score. So this is to measure error magnitude, sensitivity to outliers, and explanatory power. So as we can see, for temperature, random forest and decision tree achieve the best R2 score because of its effectiveness in capturing non-linear temperature patterns. As for XGBoost, on the other hand, it also performed well, but linear regression and SVR showed lower R2 scores, as you can see. Reason being, they may have struggled to capture non-linearities present in temperature data. As for the precipitation prediction, SVR and random forest performed really well, but SVR shows the highest performance for both MAE and RMSE because its capability to handle complex interactions within the data. As for random forest, it was slightly less effective due to higher variance in participation data. But for decision tree and XGBoost regressor showed the lowest performance, likely maybe because the tendency of overfit and inability to generalize well on unseen data. As for linear regression, it's the worst, I would say, because it assumes linear relationship, which may not hold true for precipitation patterns. And the overall comparison, random forest is rarely recommended due to the balance of accuracy and interpretability, and SVR is most suitable for precipitation. So the justification, I've divided in 4 categories, whereby contextual importance, where climate risk predictions are crucial for Malaysia due to its vulnerability to extreme weather events such as heavy rainfall, flash floods, heat waves, and so on. So the stakeholder relevance, however, on the other hand, is to use precipitation predictions to anticipate flood events in order to plan timely evacuations and resource allocations. Why am I saying that? If we can predict a certain area, let's say in Kota Kinabalu flood is going to happen, the potential victims can awake before the actual flood happens or an earthquake or something as such. So that's why it's really important as well for agricultural sector, whereby it can improve planting schedule. So if irrigation needs a crop selection, maximize yield and reduce losses. So if there's going to be a flood, it can be predicted and also can be saved before it actually happens. And as for recommendations for addressing the real world problem, we have divided into 4 categories, whereby disaster management recommendations, agricultural planning recommendations, and urban planning and policy strategic. So what is each of this category means? So as a recommendation for disaster management, we get to implement early warnings to enhance community preparedness, like what I explained previously, and also to strengthen infrastructure in flood-prone areas. So in flood-prone areas, we need more building with flood barriers, more trees so that the ground is more stronger because of the roots, and improve drainage system in order to avoid serious damages. As well, we can develop emergency response protocol before anything serious happens. As for agricultural planning, like I said, we can effectively plant and also do an harvesting schedule efficiently, and also implement irrigation system to adjust water usage based on predicted precipitation patterns, reducing water wastage. And as well for urban planning and public safety recommendations, we can develop green spaces and implement heat mitigation strategies such as reflective roofing and urban cooling corridors to protect public health. Lastly, policy and strategic intervention means that we can advocate for data-driven policymaking in climate risk management, ensuring a more proactive and decision-making, and as well as encourage public awareness campaigns to educate communities about climate risk and adaptive strategies. So that is all from my group's project. Thank you very much, sir.